Engineering. Lab setup. Instructor with whiteboard and samples of cement. Welcome to Civil Engineering Edge, your go-to classroom for civil engineering concepts and lab demonstrations. Today, we'll explore the testing of Portland cement as per IS 4031, which is crucial for ensuring quality, durability, and safety in concrete construction. We'll cover key lab procedures starting from sampling and chemical analysis to mechanical strength tests. Each test tells us something vital about the cement, whether it sets properly, develops sufficient strength, and remains stable over time. So, whether you're preparing for your engineering exams or looking to strengthen your practical knowledge, this session will guide you through all major tests step by step as done in a real lab, aligned with IS codes. Let's begin with sampling. Sampling of cement. As per IS 3535, proper sampling is critical for obtaining representative results. The purpose is to ensure the cement used in tests reflects the actual quality of the supplied batch. Cement is usually packed in 50 kilograms bags. To take a sample, select bags randomly across the consignment, typically 5% of the total quantity or a minimum of 5 bags. Open each selected bag and take to scoops from different depths and mix thoroughly in a clean, dry container. This forms a composite sample. From this composite sample, divide the cement into 3 parts using a sample divider or by coning and quartering. These are 1 for immediate testing, 1 as a reference, 1 for retesting if needed. Remember, always store samples in airtight containers to prevent moisture absorption. Visual, scooping from bags, mixing, coning, and quartering demonstration. Chemical composition. IS 269 prescribes limits for the chemical constituents of ordinary Portland cement. The key components include lime cow, silica COs, alumina alco, iron oxide FeO, magnesium oxide, sulfur trioxide loss on ignition LOI, insoluble residue. Each compound has a role in the behavior of cement. The Bogues calculation estimates the proportion of major compounds like CYS, CS, CYA, and CGAF. But for quality control, we directly measure 1. Lime saturation factor LSF. Ensure sufficient but not excessive lime. LSF equals COW0, 7SO32, 8CO to +1, 2Al2O3 +0, 6,5Fe2O3 LSF equals a frac cow, 0, 7SO2, 8 COs +1, 2 Alco +0, +1, 2Al2O3 +0, 6,5Fe2O3 cow 0, 7SO3. It should range between 0.66 to 1.02. 2. Alumin-Bayern ratio, F. FAL2O3 Fe2O3A, F equals E frac alco FeO, F equals Fe2O3 Al2O3, should be is great. 3. Magnesia MgO, should be less than 6% to avoid unsoundness. 4. Sulfur trioxide limited to 3% for OPC. 5. Loss on ignition, indicates moisture or carbonation should be less than 5%. 6. Insoluble residue must be less than 2% as it represents impurities. Visual, chemical test apparatus, titration setup, graphs of compound limits. These chemical checks ensure the raw materials and manufacturing process are under control, ensuring cement will perform well structurally and chemically over time. Fineness of cement. Fineness affects hydration rate, strength, and workability. Finer cement has more surface area, reacts faster, and develops early strength. 2 methods are permitted by IS 4031 Part 1. Sieve test. Take 100 grams cement. Use is sieve 90 micrometers. Shake for 15 minutes. The residue should not exceed 10%. B. Air permeability method Blaine's apparatus. Measures specific surface area square centimeter per gram. Based on time air flows through compacted cement bed, OPC should be greater than 2,250 square centimeters per gram. Visual, sieve shaker, Blaine apparatus working with manometer. Why it matters: very fine cement increases water demand. Too coarse, low strength. Fineness ensures balance between strength and workability. Standard consistency of cement. This test determines how much water is required to form a cement paste of standard consistency, which is essential before testing setting time or strength. We use the Vicat apparatus as per IS to 4031 Part 4. Test procedure: 1. Take 400 grams cement. 2. Add approximately 25% water. 3. Mix to paste form in under 3 to 5 minutes. 4. Fill into Vicat mold. 5. Release plunger 10 mm dia, 50 mm length. The plunger should penetrate up to 5 to 7 mm from the bottom. Adjust water percent and repeat till you get standard consistency. The water percentage at this point is known as P, used in subsequent tests. Setting time, soundness, strength tests. Visual, Vicat apparatus operation, paste mixing. Understanding consistency helps maintain uniform test results across all lab procedures. Test for setting time of cement. Setting time defines how fast cement transitions from fluid paste to hard mass. We test for initial setting time, when paste begins to stiffen. Final setting time, when paste becomes completely rigid. Performed using the Vicat apparatus is 4031 Part 5. Procedure: prepare paste with standard water P%. Fill Vicat mold. For initial setting, use a needle 1.13 mm dia. O penetration tested every 10 minutes. O time recorded when needle penetrates 5 to 7 mm from bottom. For final setting, use needle with annular collar. O set when needle leaves no impression. IS code limits for OPC. Initial is greater than or equal to 30 minutes. Final is less than or equal to 600 minutes 10 hours. Visual, real-time test demonstration. Needle impressions, importance to fast. No time for placement. To slow. Delayed strength gain, curing, temperature, and add mixtures can influence setting. Test for soundness of cement. Soundness checks the cement's ability to retain volume after setting. Unstable compounds like excess lime or magnesia can cause expansion and cracking. IS 4031 Part 3 prescribes the Lech Atelier test. Procedure: prepare a cement paste 0.78 p water. Fill Lech Atelier mold placed on glass. Cover with another glass plate. Submerged in water at 27 degrees Celsius for 24 hours. Measure initial gap between indicator points. Visual, expansion mold with calipers, boiling water tank. Then, boil for 3 hours. Cool and measure final gap. Expansion limit should not exceed 10 millimeters. Optional test. Autoclave expansion test. Measures volumetric change under high pressure. Expansion should be is less than or equal to 0.8%. Why soundness matters. Unsound cement leads to surface cracking, spalling of concrete, long-term durability issues, tensile strength of cement. Though cement is rarely used alone in tension, its tensile strength gives insight into its binding capability. IS 4031 Part 6 covers this test. We use the briquette mold butterfly-shaped. Standard ratio, cement, standard sand equals 1 to 3. Procedure: 1. Mix 200 grams cement with 600 grams. 2. Add water equals P plus 5% of cement weight. 3. Fill briquette mold, compact manually and mechanically. 4. Store for 24 hours in humid air. 5. Submerge in water for curing. 7. 28 days. 6. Test on tensile testing machine. Visual, filling molds, tensile machine pulling apart. Briquette. Minimum strength for OPC is 269. 3 days. Is greater than or equal to 2 MPa. 7 days. Is greater than or equal to 2.5 MPa. Factors affecting results. Improper compaction. Incorrect water content. Temperature and humidity. This test validates cement's bonding power vital in plaster, masonry, or small structural joints. Compressive strength test. This is the most important mechanical test for cement. It indicates how much load concrete made from this cement can bear. Performed as per is 4031 Part 6. Procedure. 1. Mix cement and standard sand 1:3 ratio. 2. Add water equals P plus for percent of cement. 3. Fill into 70.6 millimeters cube A molds. 4. Compact with vibrating table or hand tamping. 5. Store at 27 degrees Celsius, 90% humidity for 24 hours. 6. Demold and cure in water. 7. Test at 3, 7, and 28 days using compression testing machine CTM. Visual, cube casting, demolding, testing in CTM. Minimum strength for OPC, 3 days. Is greater than or equal to 16 megapascals? 7 days. Is greater than or equal to 22 MPa. 28 days. Is greater than or equal to 33 megapascals? Each result must be the average of 3 cubes. Tip: never use old or lumpy cement, it weakens results. Compressive strength forms the foundation for every RCC structure from slabs to skyscrapers. Visual. Host standing in the lab with test equipment and cement cubes around, upbeat background music. And that wraps up our complete guide on the testing of Portland cement as per its code. From sampling to compressive strength, every test you've seen today plays a vital role in ensuring that the cement you use is safe, sound, and strong enough for your structure. Whether it's consistency, fineness, or tensile strength, each property helps us predict how cement will perform in real-life conditions, be it in a dam, bridge, or residential building. These tests are not just academic, they are a part of daily practice in civil engineering labs, construction sites, and quality control units. Understanding them is key for every aspiring engineer and field professional. If you found this video helpful, don't forget to like, share, and subscribe to Civil Engineering Edge. Hit the bell icon so you never miss an update on engineering concepts, lab demos, and site practices. Have questions or want us to cover a specific test in more depth? Drop them in the comments. We love to hear from you. Until next time, keep learning, keep building. Animation and flying knowledge that builds your future.